Okay, hello and welcome everyone. This is the third in a series of lectures covering chapter 35. Today I wanted to talk about reflection of light. So, as you can see in this nice mountainscape that is being shown twice in the picture, it's because there's the actual mountainscape and there's its reflection on the water. So, light from the sun goes in many directions, and the one that bounces off and reflects off the mountainscape comes in all directions in our general direction. So some of it reaches our eyes and we see the mountain, some of it reaches the pond, reflects off, and then reaches our eye. So what we see is this reflection on the water. This idea of reflection, we've seen it already when waves on a string reach the fixed end or an open end on the string. You will get a pulse back. It will reflect back through the medium once it reaches the end. This is the same thing that happens with light rays when they encounter the interface between two mediums. Now, because light waves are actually, three-dimensional propagations, they can reflect all around space. It's not such a one-dimensional reflection as it used to be when you had pulses on a string. So, just to show this using the rays, right? You can imagine in figure A that the light rays are represented by the blue arrows. Obviously, light doesn't look like this. At least from the wave interpretation, what you get is a series of ripples. You can imagine that the general propagation direction of all these ripples is towards the glass here at the bottom of figure A, and then you see how the ripples reflect off. You should also note that this incoming wavefront, these four rays, when they reflect, the reflections parallel to each other. And if you were to do a three-dimensional graph of the glass slab that they reflect off, you can actually draw a plane of incidence where the incident rays and the reflected rays lie. And if you look at that plane is going to be perpendicular to the plane that the glass is laying flat on. So for this course, we're going to be talking about surfaces that reflect light in expected ways, which is to say they'll follow the law of reflection. So it's very, very easy to model how light's going to behave reflecting off the surfaces because the assumption is that they are smooth, they're not bumpy, and they cause what we call specular reflection. Now, again, this is a very ideal kind of mirror. Nothing's ideal, but that's what we work with, at least for this couple of chapters, as a starting model. Now, in the real world, though, surfaces are bumpy, and you have to have a really, really smooth surface where like the bumps are like smaller than the wavelength of the waves to get like full on specular reflection, But for something that's not a very good mirror, what's going to happen with the incoming light rays, like you see in figure B, is that they'll all bounce off in different directions and you won't get its reflection, right? It won't be like water on a calm pond lets you see the reflection of the mountain. But if water is very unstable, there's a lot of waves, turbulent water, then you're not going to see the mountain's reflection on it, right? The light beams hit the waves, the bumps in the water in all directions, so they diffuse away. So if you can see them between figure D and figure C, in figure C we have a nice smooth surface causing specular reflection, so the laser beam reflects off in a predictable way. But in figure D, the glass surface is very uneven, so you get this glimmer of light due to the type of reflection being diffused. This block looks fairly dusty, fairly old, so it won't act as a mirror. It's not the kind of object you want to use to build a telescope or a microscope. Now, you've seen this effect of diffuse light in quite a lot of places. If sometimes you're reading your textbook and you get glare from the lights above, it's because your textbook is kind of diffusing light, and you get this like big circle of bright light into your eye. It's very uncomfortable. And if you've seen like your bathroom mirror, like when it gets dirty, right, you get a blurry image, or when it gets foggy, because the nice smooth surface of your bathroom mirror, which is normally specular, um, has all this dust or humidity in front of it, which gets in the way. Or also, there's like roads where normally your headlights let you see ahead of you, but when the road is wet, actually headlights from other cars end up coming into your own vision, and you kind of get slightly annoyed by the fact that cars' headlights are kind of reflecting off the water, or even just walking around. So you can see in these two pictures that on a not so rainy day, the sunlight just kind of evenly kind of reflecting off this roadway. But on a rainy day, when the weather kind of remain on the surface of the road, the reflection of it is a lot more specular. So it's a little blurrier. So there's this kind of like very like shiny spots of light, or even when it's a very snowy day and it's pretty bright outside. The way that light shines is so uneven that some spots of snow can be very intense in their reflection of light, and you might want to wear sunglasses even on a cold, snowy day. But for the purposes of this course, where we're looking at a specular reflection, where we are dealing with nice, smooth surfaces, we can always follow the law of reflection to understand how light's going to reflect off. So the relationship then between incident light, which is light approaching a mirror or just some surface, some medium boundary, and the light that reflects off, is that the angle of incidence, which in this drawing we call it theta 1, is equal to the angle of reflection, theta 1 prime, just on the other side of the normal line. And when we talk about normal lines, that again from the word normal, which is right when you're normal to a surface, you're talking about some direction perpendicular to a surface. So in this case, any normal is just a line drawn perpendicular to the surface, specifically where the incident ray strikes that surface, where that's a mirror or just the boundary to some new medium like water. So you can then predict the angle of reflected rays because the law of reflection tells you that the angle of reflection equals the angle of incidence. So in movies, sometimes there's scenes where the actor just looking at the mirror, and it can be said with certainty, right, that, well, one of these things can be said with certainty. So you think about famous scenes in movies, like I think it's Al Pacino, where he looks in the mirror and he's like trying to be a tough guy. He's saying, "Hey, you talking to me?" How do they film that? Well, they have to point the camera at the mirror, right? The camera needs to see the reflection. So if the camera is pointed at the mirror, then the actor can see the camera on the reflection, standing behind them. Uh, he also sees his face. I guess A is probably true. V is kind of creepy. C would just be a blooper. So it's just that if you want to film someone's face in the mirror, then they're going to be able to see you too. There's some cool uses for reflection that might not be too obvious, but there's the idea of retro reflection, where you set up essentially kind of like 2 or 3 reflecting surfaces at perpendicular angles, so that whatever reflected beam comes towards them, those reflected beams get reflected back parallel to the original path. So they kind of act as boomerangs for light to send light right back, which you can kind of see in the bottom left figure. And this is something they've done by placing reflectors on the moon during the Apollo 11 mission in 1969. And by having retro reflectors on the moon, what you can do is you can shine a laser beam from the Earth and it'll get directed back. However long it takes for the laser to get sent off and reflected back can be used to determine the distance of the moon, which they did with fairly good certainty. Also, retro reflections good for taillights, since headlights are able to just you're able to see a tail light because your headlights, the light coming off your headlights, your beams get reflected off the tail lights back to you. You can see them. Same with like stop signs. They actually have on the surface of stop signs, you can kind of see them if you walk close to them. You kind of tilt your head a bit. There's this like small spherical bumps in some of them that have this like reflective coating that kind of turns the little bumps on the stop sign into like this little retro reflectors. And so your headlight beams or any kind of light will make the stoplight shine, so that even at night, you can see the stoplights just using your own beams. Also, right, there's like reflective panels on some shoes, or like, safety patrol vests, which means that, cars driving will be able to reflect their headlights off on your clothing, and they'll be able to spot you if you're jogging at night. It's a fairly good way to keep safe if you're a night jogger. Anyways, that's all for now. Join me next time where we'll be talking about refraction.